Hi, so here we are, part two. We're going to carry on with the calculating specific heat capacity, determining specific heat capacity from an experiment. So we're going to do some practice calculations today, and then I'm going to show you a set of results from an experiment and an actual experiment. And you will be able to hopefully use the information from that to work out the specific heat capacity of water and aluminium. But let's just check the starter. 4 questions. What is the boiling point of water? What is the freezing point of water? What is the melting point of water? And what is the condensing point of water? Just need some numbers. Pause, write down the numbers, and we'll check when you're done. Okay, let's just get this on pen mode. What is the boiling point of water? That is 100 degrees. What is the freezing point of water? That is 0. What is the melting point of water? That's also 0. The melting and freezing are the same point. If you go any higher, they'll change state, or lower, but that is the change of state point. What is the condensing point of water? It is also 100 degrees. That's just dashes, not minus. It's not minus 100 degrees. That would be completely crazy. Okay, next question. Right, so now is a chance to use the equation. I'm going to use this equation a few times. So this is just a demo, and then hopefully when it comes to the real deal, you'll be able to do it. Do you need a calculator? Which I just threw on the floor. So let's have a go. Energy is equal to mass times specific heat capacity times temperature change. The important thing is, for this scenario, the specific heat capacity for water is 4,200. So how much energy is needed to raise the temperature of 1 kilo of water by 5 degrees? So 1 kilo times 4,200 times 5 is 1 times 4,200 times 5 is 21,000 joules. It's that simple. How much energy is needed to raise the temperature of 2 kilos by 5,000? Well, that's 2 times 4,200 times 5. Well, it's the same, but double. 42,000 joules. How much energy is needed to raise 1 kilo by 10 degrees? 1 times 4,200 times 10. And that is just 4,200. Easy. Joules. Okay. Let's get this in terms of different versions. Now some actual questions. The specific heat capacity of 3 materials are given in the table below. You'll need to use these. Water is 4,200. Aluminium is 900. Mercury is 1,400. 2 blocks A and B are made of the same material, but B has twice the mass of A. If the same heat energy is transferred to both blocks, compare the temperature changes of A and B. So E is equal to M SHC times T. Okay, so it says, same material, so SHC, specific heat capacity is the same. Energy is the same, but you've got twice the mass. So let's rearrange this for temperature change. E over M times specific heat capacity times mass. E over mass times specific heat capacity equals temperature. If you've got 2 times the mass, that's a 2 on the bottom, that means T is half. So for whatever has twice the mass, the temperature change is half. Oh, I've just given you the answer. That's the question. Sausages. Well, there you go. That's the answer to the first one. Now, instead of the 2 blocks have their temperatures increased by the same amount, compare the energy transferred from A to B. Well, now you could do that one. Without doing a calculation, compare the energy needed to heat some water from 10 to 50 degrees with the energy needed to heat the same amount of water, 50 to 90 degrees. Make a comment on the amount of energy. Calculate how much energy is needed to raise the temperature of 100 grams of water by 50 degrees. Don't forget, convert 100 grams to kilograms. And calculate how much energy is needed to raise the temperature of 100 grams of mercury by 50 degrees. Don't forget to convert. So, pause, answer those questions. Good? Excellent. Right. So let's do the experiment. Well, I'll do the experiment. So, in a second, I'm going to show you a video, and then you can do the experiment. So the first one is the results for this experiment. But it's the results for this experiment if instead of having a joule meter, what we had was a voltmeter and an ammeter instead. So a voltmeter and an ammeter. And with a voltmeter and ammeter, this you measure voltage, this you measure current. In the equation, power, P, equals IV. Power is current times voltage. Once you've worked that power out, hopefully you can remember that power times time equals energy. So if we do current times voltage, we get power. If you times that by time, you get the energy. And using all of this information, we have the mass. Easy. We have the starting temperature and the final temperature. So you can use that to work out the temperature change. You have potential difference, V. You have current, which is A. And those two, you can work out P. Then with P and this time, which is in seconds, you can use that to work out energy. You know the energy, you know the mass, you know the temperature change. Now you just have to work out the specific heat capacity of aluminium. Go on. Hopefully you've worked that out. If not, take some time, pause and work it out. Now, in a minute, I'm going to show you a video, but what you need to do is you need to copy down this table, allowing you to work out the information at the end. So first of all, copy that down. Spelled. Didn't even check my. Apologies for the typo. Okay. So first of all, copy down the table. Fix that. So now you've worked this out. What I'm going to do is I'm going to show you the video. And once you've done that, calculate the specific heat capacity for water and for aluminium. So you'll have to fill in the information from the video into the table. And the last thing will be for you to calculate specific heat capacity of water from the experimental results. Okay. Okay, so going to do a simple experiment, trying to work out the specific heat capacity of water. I'm going to measure some amount of water. I'm going to heat it and then record. What I've got is a measuring jug. Measuring jug has the volume of water on the side. If you go to milliliters, so 1 milliliter is 1 gram. So 10 milliliters is 10 grams. 500 milliliters is 500 grams. Although I've got some scales as well, just in case. Let's try and get 500 milliliters. It's pretty close. That says 489 grams. Let's go for 489 grams. Can you write that down, please? 489 grams. Thank you. Have a kettle. The kettle is plugged into this thing, which is a power meter. and the power meter tells you how much electricity you're using at home. Come on, focus. There we go. So what I'm going to do is I'm going to pour the water into the kettle. I'm going to take the starting temperature, 24.0 degrees. 24 degrees. Fortunately, the kettle also, the thing has a timer on it. So if I just turn this on, you will see, there we go, it's drawing out 3000 watts. You can see the red light on the kettle. The kettle's on, it's boiling, you can hear it, and you can see it's drawing around 3000 watts. So we just have to wait a minute for it to draw all of that, and then we'll stop in a minute. $2,993. 2,993. Let's write that in the 2,993 watts. That's the average power that's dropped down to 2,995. I've gone up to 7. So it's fluctuating, but it's close. Oh, 3,000. So we're talking about around 3,000. Let's just check. We can hear it. You can see the bubbling. Bubbling is a sign it's boiling. Right. Let's double check that it's boiling. Woohoo! Steam is coming out. 100 degrees. There we go.
What?
100 degrees. Oh, got to 101, but that's some of the steam. 100 degrees. And let's have a look at the power meter. It was running for 1 minute and 12 seconds. Okay, so 1 minute and 12 seconds. What's that? 60 seconds plus 12?
60 seconds plus
12 seconds.
72.
72. Right, let's look at this. And in total is running at 243 volts. The current is not being drawn right now. The lowest power it took out was 2989 and the highest was 3041. So we can use that to work it all out. Okay, so now you've seen the experiment. You just need to fill in the table, and then using the information in the table, you're going to work out the specific heat capacity. If you're not sure, go back to the video. What was the mass of the water? You saw me put it on the scales. I even wrote it down on the whiteboard. What was the mass of the water? Don't forget to convert to kilograms. What was the starting temperature of the water? You used a little thermometer, put it in the kettle, recorded the starting temperature, put that down. What was the final temperature? Well, it boiled, so that should have been 100 degrees. So write that down. Then you can use that to work out the temperature change. Take the biggest number, take away the smallest number. What you're left with is the temperature change. The average power, that was on the little thing plugged into the wall, it was about 3,000. It went up and down. On average, 3,000 is fine. Time, how long did the experiment run for? Not the whole thing from filling up the water, but how long was the kettle on for? There may have been a mistake, may have left the kettle running too long, or perhaps should have shut it off myself, but how long did the kettle run for? And using that power and that time, you can work out the energy supplied. Power multiplied by time is the energy supplied. Once you have all of those things, you can put that into the specific heat capacity equation. You'll have to rearrange it and use that to calculate the specific heat capacity of water. The actual specific heat capacity of water is 4,200. Let's see if you come up with the right answer. That's the end. So do everything you can, and then tomorrow or the next lesson, we'll check the answers and see how we did with the experiment. Okay, love you. Bye.